Well, welcome back to the second half. We've gone from a cosmic scale to giga-light-year scale and massive black holes, and now we're sort of zeroing in on things that are closer to life on Earth, and things like star formation. So our next speaker is Blakesley Burkhart, who got her PhD from the University of Wisconsin in 2014 and does work on, she's a fellow in the submillimeter array collaboration and also a fellow, an Einstein fellow in the Institute for Theory and Computation at the Center for Astrophysics. And she's going to talk about star formation, which is actually something that I am, as a dilettante, am very interested to hear. So her title of her talk is Galaxies as Star-Forming Engines Simulating the Turbulent Birth of Stars. And I remind you to hold your questions until after the second speaker goes, and then we'll have a panel up here where you can ask your questions. Okay, Blakesley.
I'm extremely happy to be talking a little bit about my research to you today and to give you some impressions on what I've figured out in the, in this 4-panel series. I must represent purgatory. So Cora and Salvatore were representing the heavens. Now we're moving down, and so clearly at the scales of the galaxies, we've now reached purgatory. So Sarah, you have a big task ahead of you. And I want to, leave you with the feeling that, the 21st century physics that we're getting into, galaxies represent a huge enigma still. We still don't know things like how a star is formed or how galaxies evolve in cosmic time. And so today I'll be telling you more on the lines of how stars are forming and some new progress that we've made in terms of simulations and comparisons with state-of-the-art observations. So I'd like to take a step back and start with a classic. Right, we gotta go back to the classics, and that's Carl Sagan. Probably many of you at least watched Cosmos or have heard of the Cosmos program, the original one. Carl Sagan was the one to say first that we're all made of star stuff. And what did he mean by that? Well, going back to what Cora was talking about with the Big Bang produced hydrogen, helium, lithium. And where did all the other heavy elements come from? Where did the carbon, nitrogen, oxygen, all the heavy elements that make up most of the world that we interact with, and indeed our own bodies? All of this was synthesized within stars. And so without generations of stars that came before our own star, before our own solar system, we would not be here today. And so then it's a big question about the nature of our existence to ask, how do galaxies make stars? We know stars are predominantly made in galaxies. How does this work? It's important for us to find this out. And so we can take a picture of a typical galaxy. This is one of many billions of galaxies that we've observed. And we can ask about how they get gas in order to make this gas into stars. So first, we know that galaxies don't exist in isolation. So this galaxy here is actually part of a network of galaxies in the cosmos. Gas accretes onto this galaxy through a cosmic flow. And then what happens to this gas? How does galaxy turn this gas into stars? There's a whole cycle that this gas, once it falls onto the galaxy, goes through in order to become a star. So we can start with this gas being very warm and hot. It sits sort of outside the galaxy, and it cools via a number of different cooling processes into colder and denser gas. Eventually, this cold gas becomes dense enough to start to collapse under its own gravity, which we call self-gravity, and then forms these very dense clouds sort of sitting in the disk of the galaxy that we call molecular clouds. They're dense enough, they're cold enough that they're able to start sustaining molecules. And then at some point, we have this process of star formation. So, if you just think of gravitational collapse, if you continue to collapse your cloud, poof, eventually you should collapse it so much that a star forms. Okay, we don't actually know so much about that process. But okay, once you have a star, then you can have solar systems, you can have stellar evolution, and eventually the star will either disrupt its parent cloud through its own winds or feedback processes, or eventually it will explode as a supernova, and then this cycle then repeats. Okay, easy, right? We also have in the galaxy, again, it's not an isolated system. There's still outflows that are returning this hot material back to the intergalactic medium. This part here, you could say, is one big bottleneck. We still really have no idea how we go from the formation of clouds, how this cloud forms into a star. This is still a big mystery. But we do have some evidence from observations in particular that clouds are forming in what we call dense molecular clouds. These are just some of a few images, very famous images from the Hubble Space Telescope. A lot of these images were produced in the 1990s when I was growing up, and I would say images like these really got me excited to be an astronomer. These sort of images made me want to study astronomy because there's so much variety of structure that you can see here. There's so much physics going on. For example, in this one here, you can see a bow shock. This triangle shape here is a bow shock that's being ejected from a young forming star. All of this diffuse light material here is actually ionizing radiation from young forming stars. And then these dense filamentary structures are still the dense colder gas where stars can continue to form. And so there's a lot of physics going on here that we can already see in the observations. We still don't understand it very well. But we can start to speculate. How would you take these big clouds and then collapse them down to form a star? Well, gravity is probably a good start, right? So you can come up with a cartoon picture of star formation, starting with your dense, cold molecular cloud. Then you have some sort of gravitational collapse. That's radial. The cloud collapses in on itself towards the center. At some point, you reach densities that are high enough in order to ignite nuclear fusion. That's what a star is, right? So we now have fusion going on. There's some outflows. There's still an accretion disk from this original material. And eventually you start to form planets and a disk and so forth. So this looks pretty good, right? I mean, this cartoon, I feel pretty good about this. But unfortunately, the theorists had to come and ruin it for everyone with just a simple calculation. So I'll walk you through this. So we can write down the time scale it would take for a cloud of some density to collapse. This is called the freefall time. The freefall time is really just a function of the cloud density, assuming that the cloud is a spherical cloud like I showed in my cartoon. So for some typical densities of these clouds, we can calculate a time scale for collapse. And this is something like 8 million years. Now then I can say, well, I know roughly how much gas is in the galaxy. So if I look out into the galaxy, I look with the Hubble Space Telescope, with other telescopes, I can calculate the gas in the galaxy, and in particular, the dense gas mass in the galaxy, because we know stars form in dense molecular clouds, and I can estimate a mass in our own Milky Way galaxy of star-forming gas. So then I can just say, well, I want to find out the star formation rate, right? I can just divide the mass of the molecular gas in the galaxy by the collapse time in order to get a rate of conversion of gas into stars. So if I do that, I get an expected rate of around 250 solar masses per year. Now, what do we actually observe? This is what my theoretical calculation would predict. The actual observed star formation rate in the Milky Way is significantly lower. It's something like 3 solar masses per year. This is a big problem, right? We have a big theoretical mismatch between what the theorists that are studying star formation and the observers, right? And so something seems to be slowing star formation down. So we really have an issue here. So how are we going to solve this? So really, the problem of star formation is not how we form stars, right? We know gravity eventually wants to bring everything together and form a star. But really, the problem of star formation is how do you not form stars? How do you get such an inefficient star formation in our galaxy? Well, it turns out the galaxy is actually a complicated place to live in, right? There's a lot of physics going on here. This is why galaxies are so fascinating to study, is because there's so much going on here. In this galaxy here, in this picture, you've got dust. You can see these dark dust lanes that are obscuring the stellar light, stars that are producing all this bright blobs of light. You have supernovae that are exploding, that are creating extremely bright areas within the galaxy brighter than the rest of the stars all combined. Of course, planets that are around the stars. And then other more exotic physical phenomena that you've maybe heard about, like cosmic rays, right? So high-energy particles that are produced by things like black holes and supernova, or magnetic fields and turbulence, which I'm going to touch on in this talk. So there's a lot of different physics going on here. It's very complicated. So we can easily see how in my cartoon picture, maybe we missed something. Maybe we weren't thinking about something. Another complication, unfortunately, is that a lot of the timescales of galaxy evolution, of star formation, are much, much longer than our own human lifetimes, right? So I showed you the free fall time. That's the fastest that you're ever going to get one of these clouds to collapse. It's still on millions of year timescales. And so human lifetimes, unfortunately, are not so long. So how are we going to make progress here? Well, I'd like to propose to you that we really should make progress in part with numerical simulations. So these are simulations that are done on a computer where we take some known physics like gravity, like the way fluid motions work, etc., and then evolve them in space and time using computers in order to study star formation. I'm showing you a movie here, and I want to start it over. So we start with some initial conditions. So in this case, it's a spherical cloud, very similar to my cartoon picture. And then we allowed this cloud to collapse, and we also include other physics that we think are important in star-forming regions, like turbulence and gravity and magnetic fields. We then evolve this in time. Now you'll notice that time is running here. You're getting a density image here. As it zooms into the collapsing region in the cloud, because there's so many orders of magnitude in spatial scale and also in density, this color bar here, which is a log scale, so these are factors of 10, has to also zoom in. So another part of the difficulty of the star formation problem is not just the time scales involved, it's also the extreme range of scales, ranges of density. So finally we get down into the kind of densities where the star formation can actually happen, and then you can see in the simulation these star particles are starting to form in the simulation. So this is a very difficult problem, but simulations can help us understand it. Okay, so if you're going to make a simulation, right, you need a cookbook, you need a recipe, right? It's up to you. You can decide what you include in your simulation. Well, what kind of recipe would you come up with? So obviously we need gravity, right? So gravity is going to pull everything together into collapse. And the movie I'm showing you here is one such simulation that I've been working with the ENSO collaboration. And so you can see that these filaments form at the start of the simulation and then begin to collapse in on themselves. So pick your favorite part of the filament, and you can follow it in and see how it's sort of pancaking together as the simulation proceeds. So we need gravity. What other things would you include in your simulation of star formation? How about turbulence? So if you look at this initial gas density distribution, it's very fractal. It's very non-smooth. There's a lot of discontinuities there. This is what we mean by turbulence. And so for the most part, when we talk about turbulence in our everyday lives, it's usually an uncomfortable moment on the airplane when the captain comes on the PA and says, we're going to experience turbulence, and you start bumping all around and you wish it would stop. So this is random fluid motions. When we encounter this in the airplane, this makes the airplane, of course, bump up and down. This is a very nice picture by Da Vinci showing a turbulent flow. And a very similar sort of thing is happening in a molecular cloud. When we measure velocities in these star-forming clouds, we see that the velocities are characteristic of a turbulent flow, not a flow that's very smooth. And so you wouldn't want to fly an airplane through one of these molecular clouds, I can tell you. Now, what does turbulence do for us? Why do I want to put it in my simulation of star formation? Well, turbulence adds a pressure term, right? So does anyone drink coffee? Does anyone like French press coffee? Okay, when you stir the coffee around in your French press, you don't immediately push it down, right? You need to wait, you need to let it settle down. Try it. next time you want to drink a French press, stir the grinds around a lot and then try to push it down. It's very, very difficult. You've induced turbulence into the fluid, and that turbulence is providing an additional pressure term that's making it harder for you to push your French press down. So in some sense, that's a similar thing to what's happening here. The turbulent motions in the cloud are resisting the gravitational collapse, and it's not able to push the cloud in. That's the main thing turbulence is doing in the cloud. It's also doing some other things, especially on the small scales. It's actually allowing small scales to collapse even easier. But for the most part, you're adding a pressure term, so that's going to slow star formation down, right? So ultimately, we want to figure out how can we slow star formation down in order to match that 3 solar mass per year number that we sort of observe in the Milky Way. So turbulence will slow us down. What else? Magnetic fields. I bet you wouldn't have thought that, right? But these clouds are actually magnetized, and that means that we have an additional pressure term from the magnetic field that can also resist the collapse and slow down the clouds. Now, the funny thing is that when you talk to astrophysicists and you mention the words turbulence and magnetic fields, usually they run away from you very quickly. And that's because these things are very complicated. There's no full theory of turbulence from a fluid dynamics standpoint of view. This is one of the unsolved problems. And magnetic fields in a moving fluid plasma are also ugly. But we can also think of some intuitive pictures to understand why magnetic fields might be important for star formation. So for example, another real-life scenario, think about a rubber band. Right? So if you stretch out a rubber band provides some kind of tension, right? It wants to stretch back down. But with your rubber band, which is like the magnetic field lines, you can't really move perpendicular to them. You can only move things parallel to your rubber band, right? So if I take something like this, something stretchy and rubbery, I can't move my hand this way. I can only move my hand this way. And so this is very similar to what the magnetic field is doing in a star-forming cloud. And so here's a picture of that. So you have a spherical cloud, and you have the red lines here representing the magnetic field lines. So the collapse is going to only be able to proceed parallel to the field lines. The field lines are going to resist the collapse perpendicular, such that you'll eventually arrive at a situation where you have the collapse parallel to the field, and the field being slightly pinched along the perpendicular direction due to gravitational contraction. This is observed, actually. So here's an observation with the SMA telescope in Hawaii, looking at field lines in a star-forming object. And you can also, even just by eye, see this pinching effect of the field line perpendicular to the collapse. This is called a so-called hourglass morphology, or an hourglass shape in the magnetic field. And this indicates that the magnetic field is strong, okay? What does strong mean? Well, your fridge magnet has a strength of roughly 50 Gauss or so. These fields are at the micro Gauss scale, so 10 to the minus 6. And that's a pretty big difference, but for a molecular cloud, this is actually very strong. So in this case, we might expect that the magnetic forces are very strong, stronger than things like turbulence or maybe even the gravity itself. So things look very ordered. However, in other observations, so this is the observations of dust polarization from the Planck satellite, so similar to what Cora was showing, but instead we're actually now interested in what's happening in the galaxy. In this case, the fields look very random. Right? So you can see the field lines here looking very chaotic. And this might be a situation where things like turbulence, which wants to randomize the field, is stronger than the magnetic forces. So how can we further study the effects of the magnetic field in star formation? It's very complicated. We need to go back to our numerical simulations. And so I'm going to show you some very, very recent state-of-the-art numerical simulations that we've recently performed in order to study the effect of the magnetic field in a collapsing stellar environment. And we can do this, sort of in this typical way where we observe some sort of real-world phenomena. So as an example, I've shown you this instability that can actually form in clouds called the Kelvin-Helmholtz instability, where you have two shearing flows. you say, oh, I want to try to simulate this. I want to include fluid dynamics equations, mass conservation, momentum conservation, energy conservation, and I want to try to simulate this on a parallel computing resource. So we have a very nice one here at Harvard called Odyssey. And then ultimately, I'll restart that movie for you. We use a particular numerical simulation. So in this case, we've used the Arepo code, which is a code where the grid points in the simulation actually move with the fluid and change with the fluid. So they're not static, and you can actually model very precisely instabilities, turbulence, etc. So this is the code we used. This code is unique in that we are able then to, following the fluid flow as it evolves with gravity, we're able to follow it down over many, many orders of magnitude and scale. So going from 16 light years down to 100 astronomical units. An astronomical unit is about 93 million miles, the distance of the sun and the Earth. So this is a huge range of scales. We're also able to go over a huge range of densities, many orders of magnitude of density, going from the diffuse cloud scales down to the very dense cores where the stars are forming. And the original thing we've done here, in additional to that, is we have 4 of these simulations. These simulations are very computationally expensive. 4 different simulations, each with a different magnetic field strength. So we can really study in depth the interaction of the magnetic field and the collapse of the cloud. So I'm going to show you these simulations. I'm going to show you all 4 of them, and just keep your eye on the top of the screen. This is the magnetic field strength in microgauss. Here's the first simulation. And I'm going to show you all 4 in a very similar way, just to give you some idea of the scale here. So this is about 15, 16 light years across. This is the cloud scale. You can see by eye the density structure is very fractal, very turbulent looking. And this panel here, this inset here, is 1 pixel, zoomed in 1 pixel from this image here. So we're talking about huge ranges of scales. You can already see that there's a filamentary structure here, and then this panel here is even further zoomed in region where a star would be forming. Now, what does the magnetic field look like? This case has a very weak magnetic field, and if I overplot the orientation of the field lines, it looks pretty random. So the field is somewhat ordered on the largest scales, but as you go to the smaller and smaller scales, it's pretty random. It's changing its orientation at every sort of step that we go down. We expect that because in this case, we have a very weak field. Now, if we increase the field strength, so again, here's the density structure that you're seeing, and here's the magnetic field. It's already slightly, a little bit more ordered at each scale because we've increased the field strength. And we can continue to increase the field strength. So this is our second most strong field case. You can see now at the large scales, you have a very uniform, ordered field, and this somewhat persists down to the smaller fields. However, in this case, it still looks fairly random. Finally, this is the highest field strength. Things look actually quite different from the other cases. So if you compare the density fields, for example, especially at the smallest scales where stars are able to form, now there's this very nice filamentary structure that's formed in the case where the magnetic field is higher in terms of its energy than the turbulence and the gravity. And if we look at the corresponding field structure, we see that it's extremely ordered all the way down through all these different scales of star formation. And so once you get to this very smallest scales of star formation, you actually start to also see this very nice hourglass morphology that we predicted when gravity was very strong interacting with the magnetic field. So this is what the simulations tell us. They tell us that there's sort of 2 modes of star formation. One where there's random turbulent energy that's dominant over magnetic energy, and another where the magnetic field sort of dominates the collapse. This is from simulations. What can observations tell us, right? How can we better compare these 2 observations and simulations? Well, I've been harping on the advance of the simulations, that we can go through all these scales, include all these physics, but actually the observations have also been advancing. So meanwhile, we've been able to go from larger and larger scales with the observations to smaller scales. And so ALMA, the ALMA telescope, which is a millimeter wave telescope in Chile, has really opened up very high sensitivity, high resolution observations for star forming regions. And so we can combine previous generation instruments like the CARMA telescope and the JCMT telescope to get different scales of the star formation process as well. So the JCMT data is giving large scales, so sort of tenth of a parsec type scales, CARMA scales, and then ALMA scales are giving these medium and smaller scales. And so I'll show you one particular object from a recent study that my collaborators at Harvard and myself have performed using these different data sets of a particular object called Serpens 8. Here's the JCMT data, so this is something like a tenth of a parsec, down to the CARMA data, down to this finest resolution, which ALMA has just now opened up for us. And all of these data also have polarization, so they all have magnetic field orientation measurements, which I'm showing you down here. And you can see that the field looks very random. And it looks very random all the way down towards the scales of the ALMA data. So this is actually very similar to what we found in the simulations where the field is very weak. And so it seems that this ALMA scale magnetic field is not following the field from the very largest scales. That's in contrast to this nice hourglass picture. So in some cases, we see an hourglass type of morphology. That indicates the field is very strong. In other cases, like in Serpens 8, we found that turbulence is perhaps more important in shaping the field morphology. And this is in contrast to decades of theoretical and observational works, which say that you should always form this hourglass. So in this case, we did not see that. So I would like to conclude, going back to our quote from Carl, we are all made of star stuff. If we really want to understand how we got here, how our star was formed, we really have to take into all the complicated galaxy physics, including turbulence, including magnetic fields. And so it's complicated. Simulations are really going to be key to answering a lot of galaxy physics questions, star formation just being one of them. And I think really in terms of the star formation paradigm, we're going to be able to move towards a predictive theory of star formation because we understand the fluid dynamics better, because we understand turbulence and magnetic fields in a better way. So thank you very much.
So our next speaker is Sarah Rugheimer. She is originally from Montana, got her doctorate at Harvard in 2014, and is now a Simons Origin of Life Fellow at St. Andrews. I should also mention that Blakesley and Sarah do podcasts and do outreach work. And in fact, I was listening to one of Sarah's podcasts. You also do this with Sarah Ballard. And so I was listening to one of them, and she was saying to sort of, for the mental health of an academic, you should try to keep your desk clean. And I looked at my desk, and I was thinking, okay, well, I have some work to go.
I don't think I said that, though. I think it was the other Sarah.
Oh, the other Sarah, okay.
My desk is a mess.
I feel better now, okay. So Sarah's going to talk about how to detect life on another planet.
Thank you. Well, thank you for inviting me here today. I'm really excited to be talking to you about my research, which I'm interested in this question of how can we detect life on another planet. So I just wanted to start first with a question to you guys. How many of you think that we will be able to detect life in the next 10 years on an exoplanet? Raise your hand. 10 years. How many of you think it's going to be more like 20 years? Raise your hand. And how many of you think 30 years? 30 years? And like say greater than, 30, 50 years, something like that. Maybe never. All right. Well, we're going to talk about that. We're going to talk about what makes this difficult. So I'm interested in this question of, are we alone in the universe? And we've looked for various signs of life before with SETI, the Search for Extraterrestrial Intelligence. And, so far, we haven't found anything. We've just really had silence. And so my question is still, are there aliens out there? I want to know this. And we haven't yet had any sort of, greetings, Earthlings sign, and so we're still looking. And now I want to be really clear here that when I talk about are there aliens, I'm not talking about aliens. I'm not going to be talking about intelligent life today. I'm really only talking about microbes, like these single-celled organisms that we might be able to detect the signs of their life in the atmosphere of another planet. And so how could we do this? Well, one of the things to do is by looking for biosignatures. And I would argue that the strongest biosignature is something like an oxidizing and a reducing gas in combination. On Earth, that's something like oxygen and ozone, or ozone, in combination with methane. But individually, you can get either of these abiotically. For example, UV light can split water and carbon dioxide, and you can be left behind with oxygen or ozone. And you get methane from volcanism or from hydrothermal vents. And so these, by themselves, are not good biosignatures. On Earth, though, you have biology giving large fluxes of both gases, of oxygen and methane. But without biology, these gases would destruct in the atmosphere, and you wouldn't necessarily see them together in the atmosphere of an exoplanet. So this is why we go back to that definition. Also, biosignatures require context. Things like, can we get constraints on the surface temperature? Is it a rocky planet? Does it have other bioindicators like CO2 and water? Now, CO2 and water by themselves are not biosignatures because they are around in the whole universe just abiotically, but they are useful for us to detect because they indicate food and habitability and greenhouse gas on the planet. Other biosignatures that you might have heard talked about are things like N2O, methyl chloride, or dimethyl sulfide, and maybe ammonia in a hydrogen-dominated atmosphere. And these, though they're produced in much smaller abundances, are useful to think about because they don't have any abiotic known source. So my research, though, is how could we detect these biosignatures around other stars? And I love this pale blue dot image, which I'm sure many of you are familiar with, when Voyager went out past the orbit of Pluto and turned around and took this snapshot of our planet. And here it is. And in that image, you can take a spectra of the light from that and see various signs of life on our planet. In particular, you would be seeing that combination of methane and oxygen and ozone. And also we have a surface vegetation signal as well. Right now, we're not there. I just want to be clear, we're talking about future observations. So we're in direct detection, not transmission, but in direct detection, we're now detecting hot giant planets. And for transmission, we're able to do super Earths, warm, really warm or hot super Earths. So really, these sorts of observations are future. And this is just shows you the spectra of 3 terrestrial planets that we all know and love, the Earth, Venus, and Mars. And you can see that those spectra are very different. And we expect the universe to provide us with an abundance of different types of planets, and we are hoping that we're going to be able to distinguish the different types of planets by looking at something like this and getting spectra from the planets and being able to tease out how does one planet look different from another. Our first opportunity to be able to do this is going to be with the James Webb Space Telescope, launching in 2018, as well as with some of these large ground-based observatories like the GMT, the EELT, and the TMT that are being built in the 2020s. And even more so, the next generation of missions, something that in the astronomy community we term LUVOIR or HDST, is this future mission. Something that's more like a 12-meter space-based telescope. This would be able to get the direct light from these planets of habitable Earth-like planets much more easily. And so that's kind of the trajectory of where our technology is going and where we're hoping to aim our future research efforts. So my work, though, is interested in how does the star impact the atmosphere, the spectral features, and the biosignatures around these planets. And so I'm going to talk a lot about FGKM stars today, particularly the M stars. And for by and large, you're going from a high UV environment for F stars down to a low UV, though then M stars also have a spike in UV environment. And these FGKM is, again, just like bigger, hotter, down to the cooler ones, for those of you who are not familiar with that terminology. And UV destroys some biosignatures. So it could destroy, say, methane, for example, in the atmosphere, and that might make it harder to detect for us. But on the other hand, UV produces other biosignatures, like ozone, making that one then easier to detect. So UV is kind of a mixed bag in our ability to detect the biosignatures around these future planets that we're going to observe. In addition to that, it's the ratio of the far UV, so the shorter wavelength, higher energy UV, to the near UV, or the lower energy UV, that matters. And you can see this in the reaction rates for the production and destruction of ozone. So here you can see that the production of ozone is dependent on this far UV energy photons, but the destruction depends more on the near UV light, or can be produced that way. So it's not just how much UV you have in general, it's where in the UV spectrum you have. We want to have accurate observations of the star UV in order to understand our future observations. So I do modeling. This is me before I dyed my hair red. And as Blakesley said, we can learn a lot from computer modeling. This is the only time I'll be like a movie star. And so we do this to model these atmospheres of exoplanets. And we're interested in particular questions like, what wavelengths should we be looking at? What resolution should we be looking to build our spectrometers to detect these features? And how big of a telescope do we need? Do we need that LUVOIR-sized telescope? Could we go, instead of 12 meters, could we do 10 meters? And these sorts of questions are the type of questions that I hope that my work will help answer. So I mentioned, the FGK M stars, and today, just due to interest of time, I'm going to really focus on these M stars, because these are very interesting stars. So the M stars are the coolest stellar type, and they're much smaller than our sun. But they make up 75% of the stars in our universe and solar neighborhood. So in about the 300 or so closest stars to us, 246 of them are M stars. And so these are going to be our nearest targets and are just very common places that we would expect to look. I love this animation by Elizabeth here, where this is the night sky as you normally see it. And then now, if you turn on what it would look like with the M stars, I don't know if you can see the contrast now, they're starting to see more red dots there. You get to see how many more stars we would see if we could actually see these M stars in the night sky. M stars have a couple of key advantages. One is they have, because they're smaller, a similarly sized planet crossing in front is going to make a bigger transit depth. That's very useful for us as astronomers to detect planets. So you can see here's like, say, an Earth-sized planet crossing in front of an M star. It's going to create a much bigger depth than an Earth-like planet crossing in front of a star that's something similar to the sun. And so this is one reason why we want to also look at M stars. In addition, these planets around M stars, because they're cooler, are going to be orbiting at much closer distances. So that means their habitable zones are closer in, right? And so this is a diagram of stellar type here and the habitable zone. So here's, say, our sun, and here's the Earth, that's in the habitable zone. But for an M star, the habitable zones is much closer to that star. So it's orbiting maybe every 20 days instead of once a year. And if we're trying to add up especially transits, that's much more convenient for us because we don't have to wait for observations once a year. We can get them, every 10, 20, 30 days, depending on the star type. And the most exciting thing, I think, in one of the discoveries recently is that 1 in 4 M dwarfs have a habitable planet. That's amazing, because M stars are the most abundant stars in our universe and in our solar neighborhood, and it appears that terrestrial Earth-like planets form quite frequently around them. So they're good places for us to keep our follow-up. They have some problems. One is they have a lot of flares, and they might be pretty difficult places to live around. In particular, early M stars and remain active, even early M stars, which are like the hotter M stars here, remain active for 1 to 2 billion years. For comparison, our sun remained active for, say, 500 million years. And later M stars, past M4 or so in type, those later M stars remain active for 6 to 8 billion years. So this is the amount of time that they remain active with spectral type. And so that makes our follow-up and understanding what's going on is going to be more difficult. Also, M stars are just very hard to characterize in general, and there's a lot of work being done on that. So I'm going to go through kind of a little cartoon drawing of sort of the differences between what I'm going to call an active M star and an inactive M star, and then some of the observations that we have, and talk about how that influences our modeling of these planets. So this would be something like an active M star spectrum. And this is the theoretical minimum limit of activity. So that's just assuming, going back to Blakesley's point, that magnetic fields are really hard. The UV in a lot of stars is driven by magnetic field activity in the chromosphere. And say you didn't have that around an M star, you only had just the temperature in the photosphere radiating, then this would be the minimum amount of UV that you would get. But in general, when we measure these older M stars, we get something more like this, something in the middle. And we actually don't yet know what the floor of the UV is. How low can we go? Because for some of these stars, we only have the emission peaks observed. We actually don't know where the floor of the continuum is. So for example, could it be down here? Or maybe it's all the way down to the photosphere. We don't yet have that answer, and we need more observations of these stars to probe the range of expected UVs, and particularly the lower range of UVs that we might expect to get. Also, I'm going to talk a little bit about the known false positives for oxygen and ozone. So oxygen on Earth, all 21%, is produced by life, but we have thought about some ways that you could create it without life. And so these are just a handful of, the 6 or so commonly talked about false positive mechanisms. And what's really interesting about this is about, a majority of them really are most common, or we expect to be most common, or only around planets orbiting M dwarfs. So again, understanding M dwarfs and their UV is really important. And all of these mechanisms revolve around the UV environment of these stars. So I'm going to go through one example of a false positive generations of an M star. So M stars can be really, before they join the main sequence, they're really luminous. They have this superluminous phase that lasts quite a long time. They're very active. And during that phase, if the planet that's orbiting it has water, that water is going to be photolized from UV light reaching it, and it's going to break apart the water, and the hydrogen is going to escape to space, and it's going to be gone. And you're going to permanently maybe desiccate that planet. It's going to turn into like a dune world. And unless you have later water delivery, of course, but this is a concern. And if you were to observe such a planet, you might see a buildup of oxygen in that atmosphere, depending on how much of that oxygen is going to then later react with the surface, which is something that a lot of research has been going on into that problem as well. Another example this was the first example, I think, proposed of abiotic oxygen, was for planets that are just on the inner edge of before the inner edge of the Howell zone, so they're a little too hot, shall we say, and they go through a runaway greenhouse effect. So you can imagine this scenario, it's basically the same thing. You have the UV light from the star breaking apart the water, and you get the hydrogen escaping to space, and your oxygen's left behind. So again, this goes back to the point that I made at the beginning, is that to detect life on another planet we're going to need a combination of gases. One gas is probably not going to be enough. We're going to need context and multiple gases in order to understand what we're seeing. And so this goes back to the idea that was first proposed a long time ago with Lovelock and Carl Sagan, and a lot of people have talked about this with the combination of an oxidizing and a reducing gas and context to eliminate these false positive mechanisms. So And in addition to this, because most of these mechanisms rely on the UV of the host star, we really need to use real UV data in our modeling. In particular, because of the complex magnetic fields, we can't yet predict what that would be around a star, so we rely on these observations. So work is being done on that as we speak. So here is the real data instead of the cartoon, where you have, this is a bright young flaring star, 80 Leo in the black line, and this green line is a typically quiet M star. And then the red line is, again, that lower theoretical limit. And we yet don't know how low can this go, so to speak. And this difference is 10 orders of magnitude. So understanding what the lower floor of the UV is going to be really important for us, especially since we only have one UV telescope that can make those measurements, which is Hubble right now, and Hubble's not going to last forever. So when we look at these M-star models, these are, for all the different types of M-stars, going from the hotter M-stars to the cooler M-stars. The only thing I want you to take away from this here is this is on a linear scale, and this shaded region is the UV part. So it doesn't seem like it's a large part of the flux, but it's absolutely dominating what's happening in the atmosphere, because all of your photochemistry only cares about the UV light that has enough energy to break apart these bonds. So if we compare two extremes, the most maximum amount of UV that we would expect and the most absolute minimum, maybe even less than we would expect for an Earth-like planet orbiting an M5 star, you can see that the spectra might look very different. So this is the same planet just put around two different stars. So with different UV, it's the exact same stellar type, so it's the same size and otherwise star, except for just different UV. And so in the black line you have the flaring young star, and in the red line you have this theoretical minimum. And different sorts of gases build up in the atmosphere and create different features, and you could have a very different spectra, which is why characterizing the UV of the stars is going to be vital for us to interpret the signs of biosignatures and understanding the context of what we're observing in the future. So I hope I've convinced you that stellar type matters and that UV matters. And for the second part of my talk, I want to talk about how planets change. So we know that planets evolve through geology, through plate tectonics, through life. And we've, on Earth, had many different phases, going from the Hadean, hell, as I promised I would talk to about, to the Archean, to snowballers, and even Jurassic period. Our planet has gone through many changes. And I like thinking about the history of life on our planet kind of to understand the scale. It's really hard for us to wrap our head around the scale of these timelines. So I'm going to present it as if the whole history of our planet was in 1 hour. So we start at 0 minutes with the formation of Earth. So that was 4.6 billion years ago or so. Then you have the origin of life. We don't exactly know when. There's a big question mark there. But somewhere around 3.9 to 4.4 billion years ago. That's roughly 9 minutes into the hour. Then you have the oldest signs of life. That's around 3.5 to 3.8, depending on which papers you believe, billion years ago. Around 14 minutes into the hour. You have oxygenic photosynthesis, definitely has been around since around 2.7 billion years ago. That's 25 minutes into the hour. But this always blows my mind every time I think about this. Multicellular life, so anything more than just one cell, wasn't around until 1 billion years ago. It's very recent. That's 47 minutes into the hour. And land plants weren't around till 0.5 billion years ago, or 53 minutes into the hour. Humans, anatomically modern humans, so not hominids, but humans, in our anatomical form, have been around 250,000 years ago. So that's literally in the last second of this timeline. And the atmosphere, of course, has changed through all of this. So here we have no units, notice, because we can have very poor constraints on the early atmosphere. But the time, this is Earth's formation all the way up to present, and just kind of a cartoon of what we might think has happened. So we expect there was more carbon dioxide right after the planet formed, and before oxygen took hold, there was methane as methanogens kind of dominated the planet. But then once oxygen rose, the methane started declining because, again, those react together, and the lifetime of methane goes down from being 1,000 years to 10 years. Once you have oxygen around, and then carbon dioxide is decreased, and now, of course, it's increasing again due to human activity. So that's sort of what we have going on here. And oxygen has rose kind of in two distinct little steps here, and there's been some, other complexities along the way, but that's the broad picture. And so I'm going to take a look at sort of 4 time points in this Earth history, from something that's a pre-life sort of planet, something that has no just like geological gases in the atmosphere, to something with 1% PAL. So this is present atmosphere level. So that means 1% is 1% of our 21% of oxygen, not 1% of oxygen. And then likewise, 10% PAL of oxygen would be 2.1% oxygen in the atmosphere at 0.8 billion years ago, and then the modern Earth. So those are four time points. And this is where we get a little bit into some graphs. We have 4 slides of a lot of lines and a lot of graphs, and then we'll get back to some of the big picture stuff. So here is the pre-life spectra of a planet orbiting different types of stars, going from the purple colors to the red colors in different stellar types. And I'm going to go through the different geological epochs. This is the first rise of oxygen, second rise of oxygen, to the modern atmosphere. Now, there's a lot of lines there, and I don't expect you to take it all in right now, but I want to highlight a few things. One is that the ozone level pops out very early, actually, for the stars, for the planets orbiting the hottest stars, for the planets orbiting the F stars, because F stars have so much more UV radiation that they make ozone more efficiently around those planets for the same levels of oxygen. And then you see it starting to form for all stars here, and methane is, of course, changing as well in play with how much oxygen there is and how much flux we're assuming is coming from biology. And so it might be easier to detect, for example, oxygen or ozone in combination with methane actually earlier in history than in our modern atmosphere. And then you have the modern atmosphere. So that's, again, where we want a combination, ideally, of something like methane and oxygen. And this is easiest to do in the IR, though there's also reasons why we want to look in the visible as well, which we'll talk about. Also, the CO2 feature has changed as well. So the amount of CO2, of course, depends on the feature strength. But interestingly enough, you look at the bottom panel here, you have this peak. And that's due to our temperature inversion. So ozone heats the stratosphere, and then that causes an emission peak in the center of the CO2 feature. This is something that we might be able to observe, and then can be like a secondary indicator of an inversion later, or ozone in the atmosphere of a terrestrial planet. So I wanted to highlight the oxygen feature, though, and this is in the visible, because this is the one that a lot of people talk about, and a lot of missions are focused on. Can we detect oxygen around a planet? And whether we detect oxygen, just as going back to your question about the media, whether detecting oxygen as a technological goal, I think, is very valuable, but that's not necessarily detecting life, because we need to keep in mind that there's a lot of false positives. So this is something that I hope the astronomy community is going to do a very good job as we start coming and getting these first detections of potentially biosignature molecules in the atmosphere of a planet. So here we have oxygen going from prebiotic to the 1% again, PAL, 10% PAL to modern Earth. This is just kind of the absolute feature strength. But when we look at kind of what we would see with our telescope, when we add in all the fancy stuff, it gets a little harder to see, but in a clear sky model, you can still see those dips pretty well, right? Now, the interesting thing is with clouds, it really disappears. So there's a lot of lines here, but I just want you to compare. Look at, you can't really tell the dip here compared to here, and it's much more minor there than there. Whereas for the modern Earth atmosphere, you can tell no matter what the cloud coverage is. And so this is something that my thesis work showed, is that clouds are really going to be a confounding factor, and we're already seeing this in observations of exoplanets, that clouds can really block parts of the atmosphere, and this is going to be something that we're going to have to try to figure out how to get around, but it is a potential problem. And if we look in the IR, though, clouds are different because it's more based on the temperature difference between the absorbing and emitting layers. So if we look at ozone in the IR, you have the feature strength. Again, this is just the absolute absorption. Then you have the clear sky model versus the cloud, 60% cloud model. They don't look, qualitatively all that different. And so in some ways, ozone would be much easier to detect through geological time than oxygen. And so if you compare just the oxygen versus the ozone, again, here you can see that it pops out much faster in ozone than it does for oxygen. Though of course, once you get up to modern levels of oxygen, it's just there. And interestingly enough, the feature for ozone is actually deeper in the past for some of the hotter stars because the hot stratosphere actually washes out the feature. So these are all sorts of things that we're going to need to keep in mind when we're looking for these features. I just kind of want to end with like this global sort of idea of we're now at the first stage in human history that we're able to start thinking about answering this question of are we alone in the universe? And if we just think about the history of humans in 1 hour, we had the agricultural revolution. I'm starting there. I could have started 250,000 years ago, but then the clock would have been really skewed. So, we have the agricultural revolution roughly 10,000 BC. Then you have the first evidence of metallurgy around 5,000 to 6,000 BC, or 20 minutes into the hour. Written language around 3,200 BC, 34 minutes into the hour. And then the Industrial Revolution, 1760, 58 minutes and 43 seconds. The Internet in 1969, 59 minutes and 46 seconds. And the first exoplanets discovered in 1992 and 1995, 59 minutes and 54 seconds. So we're really approaching this time where I think we're going to find a lot of interesting things about our universe, as you've heard from the previous talks, and hopefully about our place in it. We have TESS launching and CAOPS launching in 2017. These are going to be great. TESS is going to find thousands of close-by planets. Dozens of these are going to be rocky and in the habitable zones of these cool stars. CAOPS is going to get the accurate radii of known planets, and this is important because then we can get the bulk density and start to figure out what are these planets actually made of. We've had some amazing discoveries this summer. The first one was this temperate planet, the TRAPPIST planets you might have heard about, orbiting a very late M star or brown dwarf, and these planets are something that maybe we could follow up with JWST, and one of them is potentially habitable. And that was very exciting. And then I'm sure you heard last month, there was even the more amazing discovery of the terrestrial habitable planet around Proxima Centauri, the closest star to Earth, which is just amazing. And I'm so excited to see what the future is going to hold for that. Ultimately, we want to be finding these molecular fingerprints of life orbiting other planets, and it's a technological challenge. It's like looking for a firefly in front of a spotlight. Imagine that spotlight's in California and we're in Massachusetts. It's really hard, but we're going to try to do it. And the first opportunity we're going to have is with James Webb Space Telescope and with these large ground-based observatories. And we live in a big galaxy, and so I'm pretty hopeful. We're one star amongst billions. We have a lot of places we can look. And we have billions of galaxies, and hopefully we're going to find some planets like Earth and be able to characterize those planets in the upcoming decades and finally answer this question of are we alone in the universe? Thank you.
Hello. This might actually be a little bit outside y'all topics, but from what I read, the planet in the solar system that, other than Earth, that's most likely to have life is supposed to be Europa because of its water and its internal heat. But obviously, that's not in the habitable zone. It's not Earth-like, obviously. So how would that change the you're not looking for the same kind of you're not looking for a model of Earth to determine whether it's whether it has life. So how does that change the process of looking for signs of life on a planet like Europa if we were to look for that? I think we're launching a craft over there at some point in the future. Look, I don't.
Yeah, I think that's a great question. It's actually a question that's very insightful because, so I would say that where life can exist in our own solar system and in the universe is much more wide areas than where we're planning to first target. If you take the example of Europa, yes, I think it is a very habitable environment because of the things you mentioned. There's water, you have geothermal activity, you have rocks and minerals. You have a very stable environment for billions of years. I'm very hopeful there. But it doesn't have an atmosphere. It's not interacting with, like if we couldn't observe that around another star system. That's way beyond our horizon. And so when we say habitable zone, sometimes it's a shorthand, I feel, for the remotely detectable habitable zone. So if we can't remotely detect life on Europa from Earth, how could we ever detect it? A Europa analog around another star system is just way too difficult. So when we're talking about biosignatures around other planets, around other stars, we're really talking about like planets that have an active biosphere that is like Earth, where there's just a lot of life on it. That's what we're hoping to be able to detect. Whereas like Mars, for example, also could be habitable, but we can't even tell if there's life on it yet, and we've sent a lot of rovers, and we have observations of orbiters and stuff like that, and we're still like, trying to figure all that out. So I feel like for these types of planets that are outside the traditional habitable zone, they're certainly interesting for our solar system search to probe where life lives and how does it arise in different environments, and can we tell if it's a second origin of life or if it was transferred from meteorites within our solar system. All of these things are fascinating for our solar system, as well as like with Titan, if we find life in the liquid methane lakes, so it's not based on water. So interesting, but again, how would we tell if that life, what are those biosignatures? So that's why we're first looking for life that looks like ours.
So I guess, does that mean so let's say we are looking on Europa, I'm sorry. If we are looking on Europa or Titan, or Mars, does that mean we're kind of reduced to just, like kind of base soil samples, like other than conjecture, we don't have much else to work on since we're not working with the Earth model as much. We're further from the Earth model.
I mean, we can go to those planets and moons,
right,
which is amazing, and we can get samples there and do, measurements in situ. And so that's what makes those like much better targets in some way. It's kind of, there's this kind of exoplanet science for planets outside of our solar system, and that's for solar system planets. I think they're both two prongs of very interesting questions, and I'm excited about all of it. Yeah.
Are there other questions? Dimitar. You'll have to get the mic though.
This is a question for Blakesley. Blakesley, I wanted to ask you a question which combines a little bit your work with that of Sarah, in the sense that now that you've shown that the magnetic field difference really matters, do you expect that there will be serious differences in the amount of mass in those protoplanetary disks around the young stars that form when the magnetic field is stronger? And do you expect this will change the planets' architectures and what planets form around such stars?
So the answer is yes. Yeah, I mean, this is still ongoing work, and the simulations I showed, sort of one of the first times that we've been able to do, multiple different magnetic field strengths. Usually those numerical simulations are so expensive in terms of the computing time you need to run them that it's very difficult to do a parameter study. So we're just now moving into this era where we can actually change all the relevant parameters and see how that affects things, like what kind of stars will ultimately form out of those different simulations. And we suspect that in the high magnetic field strength, if you remember, you could see that filament, that large filament. So more mass is concentrated into that filament. That'll change how the gas ultimately fragments into stars. And so you might get higher mass stars in that case than you would in the cases where the field was weaker and you have more filamentary structures, like smaller filaments, more fragmentation. You might have smaller stars forming. That will ultimately change what kind of star you form, which then leads into what Sarah was talking about with these different, M dwarfs or G dwarfs or K stars. That would then change the habitability as well. So the magnetic field matters.
Always does.
So one question for Sarah and the other for Blakesley. For Sarah, I guess the question of extraterrestrial life, it has multiple layers. But your signature of gas is based on the assumption that the extraterrestrial life has a similar biology to that on the Earth. That's a big assumption, unsubstantiated.
Yep.
Secondly, due to inflation in the beginning of the universe, but there may be parts of the universe in which there's intelligent life, but we will never be able to communicate with them because of a vast distance separated. But under current physical law, there's no way to communicate.
Yep.
So, and for Blakesley, because you didn't specify the time points over the evolutionary course of the universe, if you included the dark energy, I wonder if it will make a difference in the simulation of star formation on a large scale.
Mm-hmm. You mean from like cosmological scales, or? Well, so I was talking very specifically about star formation in the galaxy, but you can also think about how stars form within galaxies as a function of like longer timescales. We're talking about like many giga years, and actually the universe, we know from measurements and also from simulations, the star formation rates were much higher, 5 billion years ago than they are in the present, modern Milky Way type galaxies. So the universe, back then was actually producing stars at different rates, and we really don't understand why. So there's a lot of evidence that it has something to do with the accretion onto galaxies was higher in the early universe, but it's still an open question about what kind of galaxy physics we need to really consider in order to see the increase in the star formation rate at earlier cosmic times.
Right, and in the earlier phase of the universe, the dark energy has more significant than it is now.
Yeah.
I'm going to answer the questions as well that you asked first. So yeah, I think they're excellent questions, actually. Because why would we expect to find similar biosignatures as what we find on Earth? And a large part of this, we don't know, first off, but a large part of this relates to chemical energy gradients and things that we know work on Earth that we might expect to, through Darwinian evolution, arise. So if we look at the kind of the path of life on Earth, and just in the universe, I would quickly mention that CO2 is abundant, water is abundant. So these sorts of raw materials for life are really common. You're like silicon's less common. So these are sort of things why we might expect a life to use them, as well as water has some very interesting properties. And we have literally a lot of places to look, so we're going to look for places that we can recognize, because I just don't think we would be able to tell whether it's life or not if it's a totally different biochemistry. But I want to go a little bit further into that. Is if you look at oxygenic photosynthesis, it relies on CO2 and water and starlight. Those things are going to be on other planets, because those are both common. And so it seems to me likely that if you have some sort of life that's is able to take advantage of it, it would, because you have a lot of energy source from the star, and then you're using things that we know are common on other planets. So that might lead rise to oxygen. And then on the flip side for why oxygen is important for us, you get twice the amount of redox energy from oxygen as from the next chemical gradient. So this is what led to the rise of complex life on Earth. As for the second question, the vast distances, of course, that's going to be a problem, not just with other galaxies, even within our own galaxy. I mean, even talking to Alpha Centauri is going to be a long conversation.
Here. We have two questions up here. We'll start with one. Yeah, and then the other. Yeah.
First of all, thank you both for the talks.
Thank
Very
you.
enjoyable. I have a question for Sarah, and I'll start from very far. As an Italian, we sent Galileo to the trial. We we have a very long history of believing we are at the center of the universe, and so I always kind of rejected anthropocentrism. So for me, the question, which was the last slide of your talk, it's kind of boring. Like, just probabilistically, I believe there is life out there. So I guess my question is, what happens next? So if you think of your field in 10, 20 years, I guess that you don't want to just put a check, okay, there is life, I'm done, I retire early. So what can you do after that? What can we learn beside a binary yes or no, answer?
Okay, well, first off, getting the binary yes or no answer is going to be difficult, right? Because with these microbial signs of life, are we going to know 100% sure? We're not sending a probe there with a little microscope, seeing the things, swimming around in the ocean. So that's actually going to, in and of itself, I think is going to be really difficult, because we can only maybe say this planet seems like it has life. We can't think of any other reason through geology, chemistry, and physics alone that would make these sorts of gases in the atmosphere. So I think getting the binary answer is already actually pretty difficult, and we're only going to be able to say, maybe we think this is our best candidate. And then I think getting that answer is exciting because we don't know, right? I mean, we think life is common in the universe, and I would say I base my personal opinion on that based on how quickly life arose on Earth. We have evidence of life going back very far, so it seems that microbial life started very quickly, and so this is why I'm optimistic. But I'm very excited for us to map out not just is there life out there, but also, getting back to frequency. How common is it? How common are planets that have these sorts of atmospheres or active biosignatures or biospheres? All sorts of things that we can do with that. And then on the future horizon, I don't know, when we have like Starship Enterprise, looking at maybe different, different possibilities of biosignatures. And we're starting that work on Earth right now with looking at alternative biochemistry, stuff like what Steve Benner's working on, to see what other types of biochemistries could life use and what kind of biosignatures would those produce, and are we going to be able to distinguish that? That's much more difficult, but certainly I think that's a very interesting area of research.
As a total outsider to the field, though, I can easily imagine if we one day get to the point where we can travel to one of these planets. And actually, it's going to happen, I think, within our lifetimes, even with Alpha Centauri.
Send the little
if Breakthrough Starshot works. So if that's the case, we need to be able to somehow know something about where we're going before we go there, because it still will take 20 years for Breakthrough Starshot just to get to the nearest star system. So you don't want to somehow, stop and turn around because you realize that the planet is, not any good. So we need to be able to characterize these planets from a distance.
Yes. Yes to all of that.
I have a question for Sarah. So I was wondering, obviously, how do you take the spectrum of a planet's atmosphere? Because from Earth's perspective, it's going to be right in front of the star, and obviously the star is billions of times brighter. So how can you tell that you're getting a spectrum of the planet and not the star behind it?
It's a very good question, because it's a bit like you're getting 10 billion photons and then you get one photon from the planet. That's a very difficult problem, and when we were talking about gravitational waves and all these other very difficult measurements, this is why it's difficult, and this is why it's like looking for a firefly in front of a spotlight, across the continent. So there's a couple different ways. Really shortly, 2 ways. One is you take a picture when the planet's in front. You take it when it's behind. You subtract the two, and you're left behind with the starlight. You look at the light going through the upper layers of the atmosphere as it's in transmission, and you can measure, how it appears to change at different wavelengths due to that. And we're already doing that, actually. We're already doing that for planets that are super Earth-sized and that are a bit warmer than Earth. So we're already getting the measurements of atmospheres for planets that are very close to what we eventually want to get for Earth-like planets. So we're nearing that technological capability. And then the next way to do it, which will allow us to search for even greater number of planets, is to just block out the starlight completely with like a star shade or something on the telescope to block out the light, a coronagraph, and then you just directly get the light from the planet that's being reflected off.
Awesome. Thank you.
Another question? You have a question over here? Or 2 questions over here. It's okay.
Can you give us a little bit more of an idea of
the time scale to make the kinds of measurements that you could even be able to see let's say an ozone line in an Earth-like planet at a distance of 10 light years or something. I mean, we're talking about 500 orbits all stacked on top of each other, and so forth. And then I have a follow-up if the answer is yes.
Yeah, so there's a couple of papers, Deming 2009 and Kaltenegger 2009, look at calculating those features with JWST, and we're looking at hundreds of hours for say 10 parsecs of telescope time. So adding up multiple transits, maybe even looking at a planet for the entire lifetime of JWST every time it transits, to get a full characterization of its atmosphere. So for JWST, we're only going to be able to do a handful of these terrestrial planets. We're going to be able to do a lot of other planets with JWST. It's going to be very exciting for planetary science in general. But for habitable Earth-like planets, I think we're going to get the first glimpse there. We're going to get another glimpse with the ground-based telescopes, and then really the next generation with LUVOIR is going to be where we're going to hopefully get a more statistical sample of Earth-like planets.
Okay, thanks.
I would like to ask, maybe I didn't quite understand, but you mentioned that for the first 2 billion years we didn't have any oxygenic photosynthesis on Earth. Would you be able to detect life on a planet like that where there's no oxygen in the atmosphere?
Yeah, so I mean, so we might have had small amounts of oxygenic photosynthesis, it just wasn't widespread until, especially the first rise of oxygen 2.4 billion years ago. People argue about when oxygenic photosynthesis first started. So it would be hard. I don't think we would be able to tell, because if it was just like methane and CO2, and how much methane would you expect from geology on a different planet, that's going to be very difficult. So, that's why it is a combination of biosignatures. The other gases like N2O and methyl chloride and dimethyl sulfide and these things, they also might be around, but they're produced in such smaller quantities that they might need a much more massive telescope to see. And they're usually very individual to certain organisms rather than kind of more general to life. So yeah, I think it's going to be difficult. Certainly the easiest time to detect life on Earth was after the rise of oxygen, when you also had methane in the atmosphere, so the last 2 billion years.
So other questions? I guess that gives me the chance to ask the last 2 questions, if that's okay. So one for Blakesley and one for Sarah. So I'll just ask them both, and then you can take them. So and for Blakesley, I guess the question about going back in time to the earlier universe, I was thinking the star stuff, Carl Sagan quote, kind of pinged this in my mind. And I was wondering, the composition of the protostar clouds, if you change the composition in terms of the metallicity, have you examined that dependency, and if so, what's the result? And then for Sarah, you concentrate a lot on CO2, on ultraviolet as being a main bond-breaking driver, and I don't honestly know about ionizing radiation, but I was just curious if ionizing radiation is a factor, if the magnetic fields of the planets that you're looking at are weak or strong, or what we know about possibly the magnetic fields of exoplanets. So I don't know. So maybe Blakesley, you can go first then.
Yeah, so you raise a very good point. So if you think back to this gas cycle, where you've got warm gas transitioning to cold gas, transitioning to denser, colder, self-gravitating, and then at some point, poof, a star is formed. So the issue you raise about the metallicity affects that gas cycle very strongly, because in order to go from the warm ionized gas to the colder, denser, self-gravitating gas, you need some sort of cooling channels in order to let the gas cool down. And that is a strong function of the metallicity. So metallicity being how many heavier elements like iron or carbon or oxygen that you have. And so the metallicity is a function of how many generations of stars you've had. And we know that in the early universe, we don't have a lot of heavy elements. We have mostly hydrogen and a little bit of helium and lithium. So the very first stars, the very first generation of stars, were probably extremely different from the stars in the present universe, or in the Milky Way. The first stars had to have different types of cooling channels, and most likely they were much more massive than the types of stars that we can easily form today. And so that would greatly affect the types of simulations that you would do. So the simulations that I showed today, the sort of parameters are very geared towards local Milky Way type star forming regions, sort of similar to the Hubble Space Telescope images that I showed. There are other types of simulations, other groups that are performing simulations at very, very low metallicities, so more towards the regime of the early universe star formation. So it's also a very active area of research, and you get very, very different types of stars.
Interesting. Okay.
So detecting magnetic fields is going to be very hard for terrestrial, especially terrestrial Earth-like planets. One mechanism for maybe bigger planets and closer in could be like bow shock for the stellar wind as it's coming around in transit. But I think that's going to be very hard to constrain, actually, and that would be so interesting to know because, like you said, also, kind of protection from higher energy particles and whatnot, as well as the ionizing radiation that reaches the surface. If you look at Earth's history, most, the damaging radiation would reach the surface until you built up an ozone layer. And we know life still flourished and arose, and it did fine, whether that was under layer water or soil, or we know also that UV drives some important prebiotic reactions, as well as damaging others. So I think UV is really complex, and ultimately, though, detecting the magnetic fields on planets is going to be quite difficult.
Okay, well, thank you. So we're done with the session, but we have a reception outside with refreshments and some food. So please avail yourself, and the speakers will hang out and answer residual questions. So thanks for coming.